First of all, to start with, one can definitely use exactly the same equipment as used in the normal PV production line. You just change parameters, time, temperatures, and this kind of thing. Down the road, and this is my big expectation, this can be the driver along the old PV roadmap. If you go back 10 years, the roadmap said today cells are 250 by 250 square millimeters. It never happened because of the exorbitant price and lack of availability of solar silicon. But if you now have enough silicon supply, you can go back to the drawing board and you can move towards 200 by 200, 250 by 250 meter cells, which not only will make the production cheaper, but as well the module manufacturing cheaper. Everybody would like to have that. And with UMG material, as soon as the price comes really down, because at the moment even UMG is sold quite expensive, but based on the market, based on the gigantic production capacities that are being put on the market, the price will come down. And then you can have the market driver to larger cells based on UMG. And this is a very exciting technology because the name of the game is to bring down the cost at all levels. That's really what we have to do in the future. The second very important and for me personally very exciting direction is the use of alternative starting material. You know, we have a big shortage in silicon feedstock material for photovoltaics. There is no shortage of silicon. Silicon is the second most abundant element on Earth, and even more than 1 million ton is converted into elemental metallurgical silicon. But only a very tiny fraction, as you know very well, is converted into the highest purity silicon, which is the same used by the semiconductor industry for integrated circuits as well from the PV industry. And as a matter of fact, it's a very interesting issue because 20 years ago, silicon photovoltaics was used to use scrap material of the semiconductor industry. Of course, we got very lousy efficiency, somewhere between 10 and 13%, but this was the start of the whole photovoltaics business. But in the last 5 years, there was a time, especially between 2000 and 2003, that we had an oversupply of the silicon because after the bursting of the bubble, the internet bubble, we didn't need all that silicon for the semiconductor industry. And what happened was photovoltaics industry became lazy because they noticed that if they use this beautiful high purity silicon, it is very easy to increase efficiencies to 14%, to 15%, to 16%. Today, they are kind of hooked on this type of material, and they are very hesitant to consider that if one is intelligent enough, if one applies defect engineering, if one applies the science of defects in silicon, which has been worked on for 20, 30 years, one can actually very much reduce the requirements, the material quality requirements. And this is the topic which I find so exciting, and we are working on it at ISE very strongly. As a matter of fact, in parallel, before coming to Freiburg, I have helped found a startup company, CaliSolar, which is probably worldwide the first company and the only company at present who says we only want to make PV out of the so-called upgraded metallurgical silicon.
Well, that's a very powerful statement, and I know that Fraunhofer has spent, and yourself have spent a lot of time working on UMG.
Yes.
It's almost as if there are too many disbelievers of its capabilities, and we've had Q-Cells do a major supply contract with Timenko, and a few others have gone into metric ton levels.
Yeah.
But there is that skepticism about it. What's been the key aspects of your work, and with CaliSolar especially, now that you're saying it's not just a university, it's not just at a research level, this is going to be a real business doing this. So what's
the key aspect is the following. Anybody who takes this upgraded metallurgical silicon and puts it into a normal PV production line will experience very bad results very easily. So you cannot use this material as if it would be the high purity stuff. You really need material scientists who know what they are doing and who know how to deal with these problems. Fact is, the solutions are all there. Our research in the last 20, 30 years has provided the basis for doing this. So we don't have to go and wait for quantum leaps. We don't have to make completely new, crazy approaches. We only have to put the picture together what has science and research and development accumulated in 20 years. And if you do it right, it is easy to get very good results. And at the end of the day, it looks today as if the efficiency penalty would be just half a percentage point. So, you know, instead of 15.5% efficiency, you get 15.0% efficiency. And I think such a small penalty is easy to pay if you can increase the silicon supply endlessly. At the press conference of SEMI, the president of SEMI showed the projections for the silicon market. And according to his projection, and this was nothing discussed with me beforehand, he expects that 2012 more than half of the silicon will be alternative silicon. So we will see this very, and of course the number which he showed was 250,000 tons from today's 45,000 tons. So that is what we are facing. I cannot imagine to reach 250,000 tons based on the Siemens process, because it takes too much of investment and nobody is willing to put down $20 billion, which would be needed. But if you go this way, you can easily increase capacity very quickly. So the main argument besides price is really the capacity argument. And if we want to seriously change the world energy supply towards solar energy, we need these gigantic capacities very quickly.
Do you feel, though, that you know, the upgraded metallurgical material is like a revolution for the PV industry, or do you see it as a key disruptive material?
This depends on the perspective. For the classical semiconductor companies like the big four, Wacker, Hemlock, MEMC and Tokuyama in Japan, and REC is now a fifth big one, they are not up to now at all interested in this topic. And of course I can imagine that they will do everything to discredit this approach and say it doesn't work. Because the companies who picked up this approach are the companies who were used to selling their metallurgical silicon for $1 or $2 a kilogram. And they saw that the price of the high purity silicon reaches $400 on the spot market. And they said, why are we so stupid selling our good silicon for such a ridiculous price if with just a little bit of additional treatment we can make it sellable to the PV market? So my prediction is it will be pretty disruptive for some companies, but of course at the end of the day it will be a revolution. And at the end of the day people will say, why have we ever used this other material? Let me maybe qualify this a little bit. I expect that the future solar market will show a wide range of solutions, starting with the highest end high efficiency cell, and maybe in a moment we can talk a little bit about concentrator technology in that respect, but as well highest efficiency silicon cells, everywhere where space is a premium. Let's take rooftops in Japan. You know, I'm sure they will like to get the highest efficiency cells available on the market for a decent price. And then we go through the main market. This is the medium efficiency silicon market. This will fill the deserts of the world with solar cells. And then we come to the low end market. This is a thin film which has only half the efficiency of the good silicon. And this is good wherever the price is the only parameter. If you go into the third world, I can imagine that thin film photovoltaics will be there the main driver, because all what costs is $1 per watt and $1 per kilowatt hour. So the market will see a wide range of technologies. The market will grow tenfold in the next few years, and this means all of these technologies will make a very interesting business. You will not hear about bankrupt PV companies which have a product on the market. There will be bankrupt PV companies which don't control their technology, but not about those who have a product on the market. They all will grow. The question is who grows fastest, and this is, in my view, the market segment based on upgraded metallurgical silicon.
So could you explain a little bit about, with UMG, what's really the secret spice there? Why can this have these very good efficiencies?
Yes, I mean, at present, the normal approach, and this is the one we use in our startup, is really to simply deal with the material from the crystallization to the wafering process to the cell processing in a way which is adequate for this higher impurity content, you know. So it starts with the speed with which you crystallize. You want to make effective use of impurity segregation. Normal silicon crystal growth tries to make it as fast as possible to increase the throughput. But for this technology, you might have to slow it down to make sure you get most effective segregation. Then when you have the wafer, you will try to use treatments to extract impurities out of the wafer at that level. And we have many different approaches which can work very well. And at the end comes the cell process. And in the cell process, you must design the process to avoid that the residual impurities which are still buried and hidden in the wafer, for instance in the form of clusters, because clustering of impurities is a key word in order to make good solar cells with high impurity content, and you have to avoid that the heat treatment drives these impurities out and spoils the cell. So it's not the single one step, it is a whole food chain. And at ESE we develop as well an alternative approach, and this is to use even more dirty metallurgical silicon, crystallize it in multicrystalline way, then create wafers and use them as substrates for a very thin layer, which is a thin film technology, but which brings the same efficiency as if the full crystal would be good quality silicon. So this is as well a very exciting technology, and of course this can use the cheapest material, even less expensive than the material used in the other approach.
So we're seeing that adoption around the 15% efficiency level.
Yes.
Obviously, people are going to be very interested to know, can UMG actually gain, improve the efficiency levels over time? Have you a roadmap to kind of compete with crystalline?
My personal expectation is that we might keep that 0.5% penalty, you know.
Yes.
So right now, if you go with wonderful clean silicon into the average PV production line, what you get is 15.5%. So as techniques like backside contacts, laser-fired contacts, and all of those techniques get implemented on the high-end side, the very same techniques will be able and applicable to the UMG-Silicon. And this is, of course, the beauty. We are not reinventing the wheel, like if you want to use nanostructures, organic materials or so, where you have to reinvent the full production technology. We can, based on the current silicon PV production technology, which in itself gains a lot from the silicon production technology in the semiconductor market, and this is the reason why my prediction is so strong that the silicon crystalline silicon solar cells will remain 80%, maybe even 90% of the PV market, because of this food chain. You profit from all the stored experience in automation and cost reduction, and the same with the UMG silicon.